Probability and odds. We use these words interchangeably, like what's the probability that we're going to have a snow day? What are the odds we're going to have a snow day? And those are actually different things, right? So what's the difference? Probability is success over total, which is different than odds, because odds is success to failure. I feel like I spelled success wrong. Odds is success to failure, and then probability is success to total. So the probability of rolling a 6, well, there's 6 faces on a dice, and one of them is a 6. So you have 1 success out of 6, versus the odds of rolling a 6 are actually 1 to 5. And we tend to write odds with the ratio symbol like that, dot, dot. It's not wrong if you wrote it as 1 over 5. It's totally fine. When you roll a pair of dice, you get 36 outcomes. How many of those give you a sum of 4? Well, you could roll a 1 and a 3, or a 2 and a 2, or a 3 and a 1, and we consider 1 and 3 and 3 and 1 different outcomes. So there's 3 outcomes that give you a roll of 4 out of 36, so 1 out of 12 is the probability of rolling a sum or a 4, versus the odds of rolling a 4 are if there's 3 successes, and therefore 33 failures, or 1 to 11, or you could say 1 to 11. So odds and probability, slightly different. If you've got gummy fish and they give you the amounts there, probability of choosing a red. Well, there's 15 red. I should do it in red. There's 15 red out of, 31 fish? So 15 out of 31. And I'm just going to point out that we could also do this as this kind of problem. Oops. 15 C1 over 31 C1. There's 15 red gummy fish. I'm choosing 1, which is 15, and altogether there's 31, and I'm choosing 1. Odds of choosing a blue fish, what do we have? 6 blue fish and then 25 non-blue fish. Odds of not choosing a yellow fish, so that would mean basically choosing red or blue, so there's 21 there out of 31. Odds of not choosing a yellow fish, now it changed to odds, so that would be 21 to 10. When you go up to 2 things, and here's the thing, you're doing these at the same time. So we're choosing multiple fish at the same time. And here we use combinations. So it's kind of going to remind us of this. If we want to choose 2 red fish, it's 15 C2 over 31 C2. At the same time, right? And I've got to do that on my calculator. So again, math prob, 15 math prob NCR 2, so that's 105, over 31 math prob NCR 2, and that's 465. And then I always would want to reduce that fraction, right? So if I reduce that fraction, I get 7 over 31. If I want to choose 2 red and 3 yellow at the same time, so now I have 15 C2 and 3 yellow, so there was 10 yellow, and I'm choosing 3, and then all together there was 31 fish, and I choose 5. So I know that that's 105 from before. And so if I do the other one, 10 math prob NCR 3, oh yeah, we did that the other day, that's 120, right? And 31 C5, yikes, 169911. So I can do this as a reduced fraction on my calculator. I'm just typing this in, and then I'm going to do math change to frac. Math change to frac will reduce it for me, 200 over 2697. Okay, we're going to do the next page as well, and this is, again, on kind of compound probabilities, deck cards, all this kind of stuff. So probability, again, success over total. This is what a deck of cards looks like. If you don't know, we got the 4 suits, right? And we got all the cards. So if I want to choose a red card, wouldn't that just be 26 out of 52, or 1/2? Right? 26 red cards out of 52. Red aces, how many of those are there? Right, 2. So 2 out of 52, 1 out of 26. Then we talk about 2 events that are independent of each other, and you don't really need to know like this so much. You don't even really need to know those formulas. It's just kind of common sense. What's the probability of choosing a king or an ace? A king or an ace? Well, a king is 4 out of 52. An ace is 4 out of 52. There's no overlap between those, right? So altogether there's 8 cards that are either kings or aces out of 52. And then, of course, I could reduce that to 2 out of 13. But here, if I say a red card or a king, there's 26 red cards, there's 4 kings, but what do you have to remember? There's 2 red kings, right? And you don't want to count those twice. So you're basically counting the 26 red cards plus the 2 black kings, right? If you think of it that way, 14 out of 26 or 7 out of 13. This is the cards doing one at a time. So we're not going to use combinations here. We're going to use them as 2 separate events. So if the first card is a red king, there's 2 red kings out of 52. For the second card to be a red king, that's 1 card out of 51. Right? So this is, let's see if I can actually simplify that, right, to 1 out of 26, 26 times 51. So you have a chance of 1 out of 1,326 possibilities to get a red king followed by a red king. What if you want a king, a king, a king? Well, the first card could be a king, 4 out of 52, the second card could be a king, 3 out of 51. Third card could be a king, 2 out of 50. I'm just going to multiply those together here, and then I'll reduce it. So I get 24 out of, and I know that this is not reduced yet, 132,600. And if I reduce that fraction, I'm going to get 1 out of 5525. So use the combinations when you're doing them at the same time, and then one at a time with no replacement, you choose them as different events. Sorry, one more page, last thing. It's going to go fast though. So we did this in class where we kind of practiced these free throws with the waste paper basket, but let's say that like someone made 5 shots and they made 3 shots, right? The probability that they're going to make a shot is 3 out of 5 or 60%. And that's the probability they'll make the next shot, 60%. But let's say that they shoot 5 more and they only get 1 out of those 5. So now altogether, their new experimental probability is 4 out of 10 or 40%. Experimental probability is basically like a running total, right? Same thing with the baseball. If they have an average of 400, that means there's a 40% chance that they get a hit. And so you're like, okay, well, if they're at bat 20 times, then there'd be about 8 hits, you would think. But that's not a guarantee, right? We don't always perform at a consistent rate. Maybe the next time they get 10 out of 10. So this original was 40 out of 100. Another 10 out of 10 would be like 50 out of 110, right? 50 out of 110, I could reduce that. That turns out to be 45.45 repeating percent. So they got an increase in their experimental probability. It's basically like how your grades are in this class. It's a running total. And I know I'm going fast here, but I just want to finish out this experimental probability using the geometry. You would find the area of the big shape, in this case 72. Area of the small shape is 40. You remember from geometry that you would subtract those 2 areas to get the shaded area of 32. And then landing a dart in that would be 32 out of 72, the shaded area. And this I often do as a percent. It just seems to make more sense than a fraction, like 44% chance you'd get in the shaded area. The large circle here has a radius of 4, so I do this exact. Remember that pi r squared is the area of a circle. Area of the small circle would be 9 pi, so if I want to find the shaded part, I just subtract them, which is 7 pi. The probability is 7 pi over 16 pi, and if I divide that out, I get 43.75%. So kind of close there too. You do have a question on the test like this. I call it a dartboard question, so you might want to look that one over. But yeah, that is probability. Everything you could possibly want to know about probability.